In this lecture, we're going to now talk about the time derivatives of our translational velocities as well as our rotational velocities. Now, so if you recall, previously we talked about the time derivatives of our positions, so we call those our translational variables, and the time derivatives of our attitude or our rotational variables. And we define those each in terms of the translational velocities and the rotational velocities. So now to get the final 12 state equations, or the equations of motion, we need to now find out what are the derivatives of u, v, and w, as well as what are the derivatives of p, q, and r. So we'll define those in terms of our forces and our moments. Forces for translational and moments for rotational. So let's go ahead and jump in. So recall our aircraft state variables, right? So we defined all of our states. We know what u, v, and w are. So u is our there are translational velocities defined in our body frame. So keep in mind we have that body frame. And we also have our rotational velocities also defined in that body frame. So keep this picture in mind. We're going to first delve into u, v, and w, and then we'll jump into p, q, and r. So just one reminder about differentiation between two vector frames. So we talked about this last time, or in a previous lecture. And in that previous lecture, we talked about this vector p. If we have this vector p and we know how that vector p is changing in the body frame, well, how is it going to be changing? How do we talk about its time derivative in the inertial frame? And we went through all of this math in a previous lecture, and we came out with that the time derivative. This is the time derivative. This superscript I is with respect to the inertial frame, I frame. Oh, I should just write that as using our normal notation. And this guy right here is the time derivative with respect to the body frame. So the time derivative of p in the inertial frame is given by the time derivative of p in the body frame plus this guy right here. This is the rotation of the body frame with respect to the inertial frame. And I really should have just, it could be any two frames, but of Fi and Fb. So it's the rotation, wrote that backwards, Fb and Fi. So it's the rotation of the body frame with respect to the inertial frame. So that rotational vector crossed the vector that we're interested in, this vector p. So the time derivative of p can be written as just the time derivative with the body frame plus that cross product between omega sub bi times or cross the vector. Okay, so we'll use that especially when we jump into rotations. Okay, well, yeah, and translation, sorry. But we will use it very heavily in the rotations. Newton's second law of motion. So Newton said that we're all familiar with F equals ma, right? And it's really super simple for scalars, and it's not too difficult for 3 dimensions as well. But we have F is equal to mass times acceleration. Well, F right here, this is just the sum of all external forces. So we're going to clump all of our forces into this one vector, and in a future lecture we'll talk about where those forces come from. Okay, m, this is just mass. So m is just the mass of our aircraft. And this guy right here it's a time derivative of our velocity, our ground frame velocity. Or in other words, this is just our acceleration. So time derivative of our velocity is our acceleration. Now, the time derivative of this guy, right? We can express it, we can break it up in terms of the time derivative with respect to the body frame plus this cross product term that we just spoke of. So that's really nice. We have mass times the time derivative of, we're just substituting this guy in, right? So this relationship, we're just substituting in, is equal to our sum of our forces. So, not too crazy. Let's apply it, or let's keep working it out. If we express it in the body frame, now when we express it in the body frame, that's really nice because then this guy, remember it's our ground frame velocity, this just becomes UVW, right? And in the body frame, our rotational vector, well, that's just our P, Q, and R. So these are things that we already know, right? And then we have the time derivative of that with respect to the body frame, and we'll jump into that. But we already know these things, and we're going to just clump up. We're not going to worry about what our actual forces are quite yet. We're just going to clump them all up, and we'll separate them out into our X component, Y component, and Z component in the body frame. Now this guy right here, this is VGB, the time derivative of that, right? And it's in our body frame. So if we look at that, this guy, it's just going to be the time derivative of U, V, and W, which is fantastic because we already have those in the body frame. Or that's already our V sub G in the body frame. So that's the thing. This guy right here is what we're trying to solve for. We want to know what our time derivatives are of U, V, and W. So we can then solve for these guys. It's pretty easy. We're just going to move things around. We're going to take these guys, move it to the other side, and divide by m, right? So we want to move them. So it's just a little bit of algebra at this point. So we say, hey, we want to have U, V, W dot. That's going to be this term right here comes down. We're just crossing P with our velocities. So this is our rotational velocities, right? BI in the body frame, and this is our VG in the body frame. So we're just crossing those. We get the 1 over m times our forces from just dividing things out. So fantastic. If we take the cross product, right, this is just right here, BIB cross VGB, and I wrote a Q, but that is definitely a G. Right, so it just simplifies into that form right there. So that's fantastic. So now we have our translational velocities in terms of states, and in this case, if you recall, this is what we're going to consider for chapter 3. These are inputs. Chapter 4, they'll be a function of our inputs. Okay. Excellent. So we've done our translational dynamics. Now let's jump into the rotational. And again, we're going to use Newton's second law, where the h is our angular momentum vector. We'll jump into that a little bit more. So the time derivative of our angular momentum is just equal to the sum of the moments. So we have our external moments. That's what this guy is. Not to be confused with mass or any of our other variables m. So it's usually pretty clear by context. And in this case, we have a bold m. So we're going to take the time derivative again with respect to the inertial frame. So in our inertial frame, that time derivative of h is equal to the sum of all of our external moments. So we use that relationship that we talked about previously, right? All we're doing is relating, determining what that guy is right there. And again, it's going to be because we have body elements that we're really wanting the time derivative of our body elements, right? So we have dH dTB, so the time derivative with respect to our body, plus, and this is the same relationship as before, we're just doing our rotational velocities cross that vector h. And we'll set that equal to the sum of our moments. And then we can express that, all those variables, in our body frame. So once we express them in our body frame, now we can start to play with them. In a rigid body, the angular momentum is just defined as the product of the inertial matrix and the angular velocity vector. So this is a definition that we're going to get. So h super b is really straightforward to define in the body frame. Or h is really easy to define in the body frame. It's just equal to our inertia matrix multiplied by our angular velocity. So that's fantastic. These guys, the inertia matrix is well defined and studied. If we were to look at these diagonal terms, these are called our moments of inertia. So if you hear that term, and the off-diagonal terms are called our products of inertia. So in terms of this class, this is about as far as we'll go in terms of defining J. We'll do one more simplification. But our J is usually determined either by a CAD program, once we've modeled the vehicle and the densities of the materials and things like that. Finite element analysis can be done to determine what our J matrix is, or we can measure it experimentally. So at the end of the day, though, what we care about is the fact that we have J. So that's a nice term, or a nice thing. So J is, for us, this is considered a given constant matrix. So some parameters we define in a parameter file. Okay, as we look at the rotational dynamics, coming back to that, we're going to come back to this equation here, right? So all we're doing is restating that equation. Now we're going to start plugging things in. So the time derivative of this guy right here, right? That's in the time derivative with respect to our body. So if we look at this thing right here, so if we do dt in terms of our body, so we're not considering the rotations of that body in this operation, right? Of J times WBI in the body frame. Well, J is considered a constant matrix. So we can just pop that guy right out, and we get this is equal to J times the time derivative. Wow, that was not at all the time derivative. Time derivative with the body with respect to WBI, which is equal to J times, now we have P, Q, R, time derivative of these guys, which this, right, this is what we want. Okay, so coming back down, that's all you're seeing right here, is that we've taken this guy out, we've defined it in terms of the time derivative, and so we still have our angular velocity vector crossed with hb. Well, now we've just plugged in what is the value for hb that we defined up here, right? So all we're doing is plugging those things in. And again, our moment vector, we're just going to assume it's given to us. So that's going to be one of the inputs to our system. So we're going to rearrange. All we're going to do is multiply everything by J inverse, and then get everything else on the right-hand side of the equation, except for the things that we care about, which is PQ and R dot. So we have PQ and R dot, which is what we're trying to find. It's just equal to, and we could almost call it quits right there. We can find that, or that's what our time derivatives are equal to. We're going to do now just a couple simplifications. The first one, we're going to look at J inverse to look at that. And then number two, we'll expand this out a bit so that we can see things just a bit better. Excellent. So let's look at our rotational dynamics. If we look at our aircraft, it's typically symmetric, or yeah, it's almost always symmetric about the IK plane. So if we pull up our aircraft, right, all this is doing is we're defining a plane, that's cutting our aircraft down the middle. And if we go to and I guess we would, right, it's up in the K. So this is the I, and this is going in, well, I drew K in the opposite direction. But we're just looking at that IB plane, and if we take left or right side of it, our aircraft basically looks equal, right? Especially if I had drawn that straight down the axis. So coming back down here, what that does is that that causes elements of J to be equal to 0. So the XY and the YZ then are equal to 0. And J gets simplified just a little bit. So the symmetry helps us to define the inverse. We can, a 3x3 matrix, we can always take an inverse. We can define what the inverse of that matrix is, whether or not it exists. Depends on whether or not our matrix is non-singular, but we have nice formulas for an inverse of a 3x3. So no big deal, but if we have this nice form with these zeros in a very symmetric pattern, we can define the inverse of J. And again, it's the inverse of a matrix is just the adjoint over the determinant. Not super important for you right now, but that's what we're expressing. We have the adjoint on top over the determinant of that matrix, and this allows us to write our matrix here where gamma is just a constant, right? Gamma is just defined as that constant variable. Okay, so we can express J inverse fairly nicely just by taking into account that symmetry. All right, so we're going to define. Now we'll simplify everything out. The first thing we define is our moment vector. We're going to define that as L, M, and N. Now again, do not to be confused with mass. This is the moment about the y-axis in the body frame, right? So another thing we're going to do in terms of notation, we can write a cross product. This is often denoted as omega hat or other terms, omega plus. But anyway, so we have this omega hat term where we form a matrix out of a 3x3 skew symmetric matrix out of our vector A. And that allows us to write the cross product really easy as the cross product turns into a matrix multiplication, which is really nice. Okay, so now this is from before. We haven't done anything. Now we're going to start to put everything in, right? We've taken J inverse. We defined that on the previous page. We'll take this cross product. We're just taking this matrix definition of our cross product here. And we're going to put our PQ and R become that A vector. And then we're going to multiply that by J times W sub bi in the body frame, right, which is just P, Q, and R. And then we use this definition of our mass to, or not our mass, it's not to be confused with our mass, but our moment vector, and we plug it in. So the following two lines, this is just algebra in that line. And this one, we just define a bunch of constants. We define our gamma 1 up to gamma 8. These are just constants that we've defined on the next slide. And we can see that our P dot, Q dot, and R dot are now functions of all of these elements. So it's functions of our state. Recall that our state that comes into play here is P, Q, and R. And our inputs, again for chapter 3, are we have L, M, and N. Okay, now in the previous lecture when we looked at the simulation, we were able to see that when we did, even though we say that L, our moment about the x-axis, is largely affects rotation about the x-axis, we saw that it started to wobble. The aircraft actually started to wobble when we saw non-zero terms, right? And that's because when we apply L, we have this really strong term, but we also get in, oops, sorry. L also, let's see, just a sec. L is going to affect P. Sorry, L is not one that affects, oh, L does. L affects our Z directly, right? So we directly affect our R dot. So L is directly affecting R dot. And then if we look at indirect actions, so L directly affects both P and it also affects R. So if we look at here, we have effects on P and R, right? So P and R are changing as well, which will then cause basically some wobble in the other frame as well. So we can see that the fact that even though our moment is largely, I mean, it's applied to that the one axis, we can see how it has direct and indirect effects on other axes, or the rotational velocities of other axes. Okay, so now we have our full 12 degree of freedom model, which is really great. They're expressed in terms of first order ODEs. This is often referred to as a simulation equation, which we'll get into in a future lecture. But we can now take those ODEs and we can simulate forward in time, where again, our states, our x is equal to Pn all the way down to R. And our x dot then is equal to, we have Pn dot all the way down to R dot. Okay, our inputs are going to be our force in the body frame, which is equal to Fx, Fy, and Fz, and our moments in the body frame, which we call L, M, and N. Okay, so these are our inputs according to chapter 3, right? Those are the inputs to our system. So given our forces and given our moments, we can describe exactly how our system is going to be moving and rotating, which is really fantastic. And again, like I mentioned before, we have these constants are now just defined, and we see how that how our J matrix comes into play. Excellent. So now you have all 12 degrees of freedom, and you can simulate your system.